A long time ago, two massive black holes collided and they produced such an amount of energy that they generated what we know as gravitational waves, which are like ripples in spacetime which contract and stretch space as they propagate outwards in all directions. Now, it's important to know that everything generates gravitational waves, but we needed a cataclysmic event because only such a colossal amount of energy would generate a gravitational wave big enough to be detected by us. Gravitational waves had been theorized, but they hadn't been observed until the 24th of September 2015, when these waves passed through Earth and we managed to detect them with two incredibly precise devices called LIGO Hanford and LIGO Livingston. But how? How do they work? Well, gravitational waves are tiny, really tiny. 10 to the minus 18 meters, that's 10,000 times smaller than a neutron. So, to measure such a small distance, LIGO has two perpendicular arms, each of them 4 kilometers long. Those arms have laser beams traveling through them. The idea is that one of the arms would get longer than the other when the gravitational waves came through, and so the two laser beams, which interfere constructively, would get slightly out of step and cause the detector to detect less light than usual. That's all fine, but the issues have just begun. For this to work, you need a perfectly stable light beam that doesn't change its frequency, and to avoid uncertainty, the solution was to make the laser very powerful. So the laser's power is a megawatt, and if you don't know how much energy a megawatt is, that laser would go through you if you were to stand in front of it and vaporize your body. So that's a lot of energy. Furthermore, to avoid interferences, the air was sucked out of the arms of the detector, but this raises the question: how did they know that what they detected wasn't an earthquake or another unrelated event? Here's the answer. The mirrors used to reflect the lasers are the smoothest mirrors ever made, and are suspended from silica fibers hanging from a quadruple pendulum to eliminate any outer source of vibrations. So yeah, detecting gravitational waves is as easy as having two identical detectors with two forks on it. That seems like a lot of trouble to detect such a tiny thing. So why do we even care? Gravitational waves give us another way to look at the universe, because up until now we could only gather data from what we saw. For instance, we now know that two black holes collided and generated these gravitational waves without witnessing the event. No more need to stare at the night sky hunting for supernovas. With detectors a bit more precise, you could just detect their gravitational waves. And same goes for black holes, binary star systems, and much more. So, you could say that gravitational waves are, though tiny, a very big deal for learning about our universe.